Okay, thanks. Thanks for the introduction. My name is Yubo from Huawei, and very happy to be here to present our work, the FlacIO, a FLAC and collective I/O solution for container image CV. Okay, at the beginning, I want to introduce the traditional storage stack of the container image CV. So we can see the container will build their root file system on the overlay FS, which is used to merge multiple layers of the image and show a uniqueness base for the container. And a native solution of starting a container is to load the full image to the host node. However, this solution is very inefficient because it will bring dozens of times the I/O application. And the first optimization in current world is to accelerate the code startup. For example, the lazy loading is a mainstream solution. It only fetch the metadata of the image to the host node and start the container instantly while they perform the data I/O on demand during their running. And another optimization is to mitigate the code startup. Such network use the host size catching, sharing, or maybe the forking and P2P loading to remove the code startup overhead from the system. However, such network need the host resource, and the host resource is limited, as we know, so they cannot fully solve the code startup problem. And this work will focus on the code startup acceleration. Okay, let's take a look at the typical process of lazy loading. At the first stage, it will obtain the metadata required for building the container runtime. Then it will create the runtime in the host, such like creating the C group, creating the root file system. And in the last stage, it will launch the service and execute the entry points in the container. And as we can see, the data will be pulled to the prefetch cache in the lazy loading module first, and then load to the local file system. At the same time, it will trigger a lot of network I/O in this stage. Okay, now let's break down the overhead of the code startup in existing solution. And in our experiment, the CRFS and Ning are file level lazy loading system, while the DADI is a block level lazy loading system. And from our result, we can see the lazy loading solution can speed up the deploy stage, but they suffer from a very long latency in the ready stage. And when we go deep to analyze the I/O behavior of existing system, we found that they suffer from a serious I/O amplification and inefficient network access in their ready stage. Okay, now we found that the key cause, the root cause of that bottleneck is the image abstraction. So in the traditional image abstraction, it's global oriented. It means that one image is used for multiple services. And it's also a storage oriented. It means that it records the disk state. So the shortcoming of this abstraction is that it makes the lazy loading system hard to aggregate the I/O due to random access on the image, and it will lead a high I/O amplification due to the mismatch between the lazy loading unit and the container I/O size. At the same time, the I/O locality is difficult to optimize because the I/O behavior are different across the CV. And finally, it needs a complex I/O path to convert the disk state to the memory state. Okay, so we propose a runtime image abstraction. And the key idea of the runtime image abstraction is to preview the memory state for each service. So it is a service-oriented, means that one image is used for one service, and it's memory-oriented. It only records the memory state rather than the disk state. Okay, so the benefit of this abstraction is that it is network-friendly because it can accurately raw the data for code startup by a single network I/O, and it also gives us opportunity to support fast root file system construction. Because the runtime image already contains both the index and the data of the memory state, so which allow the root file system can directly be mounted on a given runtime image. However, the FlacIO design is non-trivial. We meet two challenges. The first challenge is how to organize the runtime image in an efficient manner, and we should consider the correct accurate the I/O chasing during the container startup, and it should be compact in the size, and also to be compatible to the ecosystem. And the second challenge is how to build a lightweight I/O stack on the host. As we know, current kernel does not support to mount a file system from a given memory state, so we need some new OS primitive for it. And at the same time, the FlacIO run upon the lazy loading system, so it should be compatible with the legacy I/O stack. Now let me introduce the overview of FlacIO. It includes 4 key components. The FlacIO driver play as a control plane to bridge the other components in the system, and the I/O checker is used to record the I/O during the first time the container is started. And the runtime page cache, or RTPC for short, is a special file system page cache in the kernel, which allows the runtime image to be injected to the kernel and mount to the root file system. And finally, we have a runtime image service in the registry node. It used to manage and generate the runtime image. Okay, when the user calls the runtime image creation API, it will launch the container, collect the I/O, and send the I/O trace to the registry for offline generation. And during the code startup, the FlacIO driver will get the runtime image metadata first, and then it will pull the image data by a large network I/O, and then inject it to the RTPC. And during the container running, the RTPC handle the read and mmap page flow of the page located in the runtime image, and also for the I/O that missed in the runtime image, it will be redirected to the normal process. Okay, now the runtime image generation rely on the accurate I/O chasing when container is cold startup, right? So in fact, I/O chasing is not a new thing. For example, DADI use a block level chasing mechanism for I/O prefetching, and it used a BLK trace and the FIO to record and replay the I/O respectively. However, we use the pop-based and file level I/O chasing mechanism, and the end user may use the RT-create API to generate the runtime image, and it includes 3 parameters. The image name and the entry point are used to calculate the unit service ID, and the POP it used to tell the I/O checker when to stop chasing. Okay, and the POP has 2 types. In the external type is such like is a program run outside the container, like the HTTP detection, and this is very useful for some network service container like Redis and Mcached. And another type is the internal POP. Internal POP is run inside a container, like an entry point of the container. For example, we can use importing the core library as the POP. So this way is very efficient for some framework container, like the PyTorch and TensorFlow and the other one. So when the CT create is called, it will start the container for chasing, and we use eBPF to record the read and the page flow I/O under the container namespace. Then finally, the I/O chaser will send to the registry for the offline generation. And the advantage of this design is that it's more accurate than the previous solution, because we can stop chasing when the POP captures the corresponding event. At the same time, it's suitable for any lazy loading system because it implemented in the VFS layer. Okay, here is the runtime image organization. Because the runtime image is a per CV, so if we don't concern the data duplication between the runtime image, it may dramatically increase the memory usage in the host node, right? According to our analysts, the duplication rate is very high between the service use the same base image, but it is very low if the service use a different base image. So we propose the group structure. It consists of the service that belong to the same base image, and the data belong to the same group will be duplicated and stored in the data zone. And the data of the runtime, the service metadata is private for each runtime image, and it records the file index and the page mapping of the group data zone. And to support deduplicated, it uses a bitmap to record the distribution of its data on the group data zone. Okay, the runtime image generation is performed in the registry offline, and when it receives an IO trace, it will initial the relative metadata and the group metadata. Then it will phase out the page in the record from the base image, then calculate the fingerprint of the page and check it if it exists in the data zone. And if the page is a new page, it will update the duplication fingerprint and add it to the data zone. Finally, the page table and the bitmap in the service metadata will be updated. Okay, during the cold startup, the FlacIO first get the service metadata from registry and call a new OS parameter, the RTDiff, to obtain the prediction of the mistake page. As the figure shown, each group relates to RTPC in host, and each RTPC maintains a bitmap to denote which pages are already logged. The RTDiff will return a diff bitmap by comparing the dzone bitmap in the service metadata and the bitmap in the host RTPC. And by sending the diff bitmap to the registry, the mistake page will be pulled to the host and inject to the kernel. Then we use the RT inject to load the service metadata and mistake page to the kernel. Finally, the container platform will use a special mounting flag to build the rootfs based on the runtime image, and it search the runtime image and then point the file system superblock to it. Okay, the file system in the RTPC is simple because the RTPC is on read-only cache, so we only need to handle the read and map page fault for the page that located in the runtime image. In the file open, it will search the file index in the service metadata and point the inode to the corresponding page table. And in the file read and map page fault, it will search the page table and then return the result, or if the page is not exist in the RTPC, it will roll back to the traditional VFS process. Okay, let's put everything together. Now, FlacIO is in placement in the open OILA, and we port it to two mainstream lazy loading systems, in CIFS and Nindas. And we customize the plugin snapshotter in the container D for each system. The process in the figure show the workflow, and FlacIO can start to load the metadata, the data, and perform the injection only after the image manifest is logged. And so many FlacIO processes can be overlapped by the container platform process. An existing lazy loading system also use some prefetch optimization compared to the explained prefetch. It just simply explains the loading unit. So it is rely on the I/O behavior of the container to be strong locality. And compared to the prioritized file prefetch, it is strong relies on the user experiments, and it has a very large loading unit. And compared to the trace replay, it does not well adjust the problem of accurate tracing and efficient aggregating. In contrast, FlacIO is more accurate, more efficient for I/O aggregation, and more lightweight. Oh, okay, now I show some evaluation. I will run the host on the server with 24 cores and connect to the registry by 10 GB network. In FlacIO, we use the internal POP for PyTouch and TensorFlow. We set the POP as loading their core framework library, which means the tracing window will end of the successful loading the core library. For other container, we use the HTTP detection as the external POP, which means the tracing window end of the successful access of their service port, like return the HTTP OK. And the result so that FlacIO can improve the performance by up to 2.7 times in cold startup compared to the second best system. And in addition, for warm startup, comparing the system with and without FlacIO, it almost no additional cost. Okay, so next I show the network and memory overhead. From the result of TCP dump, we can see FlacIO reduce the network data volumes and the package number by more than 1.6 times in the PyTouch container. And in the DRAM footprint, FlacIO also DRAM friendly. We can save more than 70% memory footprint compared to the other system. And the reason is that we have a lower I/O amplification and we have a shorter cache layer. Okay, now let's talk about the trade-off. The main trade-off of the FlacIO is the backend storage overhead. So we generate the runtime image for 9 mainstream container and calculate the overhead. And the results show that the runtime image account for 9% and 4.7% of the total size for the CFS and Indus respectively. And we can summarize that FlacIO can pay around 5% of storage overhead for up to 2.4 times speed up in the cold startup. And at the same time, the storage overhead can be further reduced by the compression. Okay, finally, we evaluate FlacIO in some real-world application. In the object storage scenario, we launched the MCACHD and performed the object injection. And the results show that the FlacIO can make the object storage warm up faster. And in the machine learning training scenario, we start a TensorFlow container and train the minutes data set with CurlOS in TensorFlow. And we can reduce the on-demand loading cost during training, so finally reduce the training time. And in the auto-scaling scenario, we start 64 Postgre container in A-node cluster, and the results show that FlacIO reduces the tail latency of dynamic expansion by more than 22%. Okay, conclude. This paper analyzes the bottleneck of the existing lazy loading solution, and then we propose a runtime image. Then we design and implement FlacIO based on the runtime image. And we adopt the FlacIO to 2 mainstream lazy loading systems, and the results show that FlacIO can significantly accelerate the cold startup. Okay, thank you.